So not necessarily part of the notes, not worth writing down. Quick recap of where we've been just to build up some momentum. So we had this rule, integral from a to b of x dx. We ended up with squares over 2. The b squared would be subtracting the a squared. We had this rule with x squared, then it became cubes over 3, where we did the b stuff minus the a stuff. I would guess, without me telling you, you could probably come up with a rule for x cubed based on pattern.
B to the 4th over 4.
It would be stuff to the 4ths over 4. And it's the b stuff minus the a stuff. I would guess, if I gave you x to the 10th dx, you could probably come up with a formula for that.
Stuff to the 11th over 11.
Stuff to the 11ths over 11. And I referenced a few days ago the fact we don't want to have to write a rule for like literally every possible thing. It's just not practical. But somebody sort of sensed the pattern here and said, hey, wait a minute, we've seen this before. We've turned x squared into x cubed over 3. We've done that. That had a name. That was a thing. Do you remember what that was? That was called the antiderivative to us last chapter. So somebody at some point in history figured out an integral is just an antiderivative. So the way that they would write this is they take x squared, instead of writing the rule out this way, the antiderivative of x squared is 1/3 x cubed. And then they're going to put a little brackety thing with an a and a b. That means it's time for us to plug things into this. The b is always going to plug in first. The a is going to plug in next. And we'll do a subtraction, upper limit minus lower limit always. Instead of writing this, I would write something like it's 1/11th x to the 11th. And it'll be time for me to plug in a second from a to b. I'll do the b's minus the a's. So you're going to see this kind of punctuation for me a lot, this little half bracket. So we'll take a walk over here. What these are called are definite integrals. Tomorrow we'll do a thing called indefinite integrals, which will be easier than definite integrals. That doesn't sound like it would be true, but it's true. Indefinite sounds like a bad word. Indefinite will be a good word. So today we're doing definite integrals. Definite integrals mean we have numbers here. So if I ask you to do the definite integral of some formula that I'm calling f, we're going to turn in another formula that our book calls it capital F, I guess just to be confusing. I might have chosen it, maybe I should have chosen a different letter because I guess I'm running this lesson, not the book. But they're going to take an original formula and turn it into a new formula. And they're going to plug in the upper limit, they're going to plug in the lower limit, and we're always going to subtract the results. Upper limits result minus lower limits result. And we already gave away the magic word. This new formula that I'm calling capital F, that I'm plugging into, is just the antiderivative. As the year goes on, I'll say integral more and more and antiderivative less and less, but those are synonymous words. And whenever they figured this out, people were sort of startled by that accomplishment, that derivatives were doing slopes and the antiderivative did areas. And they were like, wow, that's interesting. They didn't see that coming, but it came. This is also handy for the purposes of your card, because now you have a symbol that you can put things on your card. Like you can write that the derivative of sine is cosine. Now you have a symbol that you could also express that the antiderivative of cosine is sine. And you could write that both ways if you want to. Or you could do what you've probably been doing in the past, where you look up the derivative rules and try to run them backward. Now you have like a symbol that you can use to like express yourself forward and backward by two different symbols. But here we're trying to do the antiderivative of cosine, which I just gave away, is sine. And for the rest of the year, if you're like me, this will probably give you pause like, because the derivative of sine is cosine, but the derivative of cosine is negative sine, which means the integral of sine is negative cosine. And I always have moments of pause, like, I know there's negatives involved, and I have to like sometimes just stop and think, is this the direction that I have to switch the sign or not? Because like sines become cosines and cosines become sines in both directions, but one direction switches signs and one doesn't, depending on the work. But first thing we'll do, just do the antiderivative, and then we'll write this little bracket. And we're going from 0 to pi. So for conversation purposes, the answer is going to be, like 1 or something. For conversation purposes, if you're like, I didn't get 1, how do you do that? I say, okay, was your antiderivative sine? Oh no, I had negative sine. You want to write down what the antiderivative is and then plug into that. I'd rather plug in sine of 0. I just have to make sure I put that second. But sine of 0 from your chart base, do you remember?
0.
It is 0. Pi takes a little bit more of a thought investment. In the world of 0, 190, or 0, 90, 180, 70, 360, all of that, pi is the same as 360, 0. They all share an axis because pi is 180. So they all share those chart answers. So sine of pi is actually also 0. And you're doing 0 minus 0 to get 0. That wasn't that exciting. But in another problem, maybe you got root 2 over 2s and root 3 over 2s, stuff we could maybe deal with. Concept is, do the antiderivative, and then it's plug in time. Upper number minus lower number. Okay with that? So what we just did is we opened the door to being able to do tricky stuff or more complicated algebra kind of stuff. So if this is my homework problem, I would not write it down as is. I'd write down the root x as x to the half. I'd write this as 4x to the negative 2. And then we'll just do our thing. Antiderivatives, the powers go up 1. So this would be 3 over 2. And then you divide the old number by the new power. And this would have a 2/3. Divide the old number by the new power.
9 over 4.
Because when you divide,
Flip.
what?
Oh, 1.
Be a 1. This will rise by 1. Careful on negative pound. When you rise by 1 and negative pound, it's a little bit weird feeling.
Negative 3. Or negative 1.
Negative 1. And then divide the old number by the new power.
Positive 4.
Positive 1. And then we'll write our little like brackety, it's time to plug in. When you go to plug in, you might prefer to like retransition back. This would be a square root of x cubed. This would be a 4 over an x. You might feel more comfortable in plug-in territory reverting back. But when you do the antiderivative, do the integral, I think you want to rewrite those. So 4n, 4 rooted is 2, cubed is 8, plus 4 plugged into this is 1. That's the result from the beginning. Minus 1 to any power is 1, plus 4 from dividing. 9 minus 5 is 4. Okay with that? Then I'm doing homework problem number 25 for free for some reason. So new homework page is working from 309. 309 is going from 1 to 30. 1 to 24 should be about like what we just did. Some are a little bit harder than others, but the concept of 1 to 24 is do the antiderivative and then plug in the numbers, subtracting the upper numbers result minus the lower numbers result. 25 is like a retread of yesterday, so here's 25 in case yesterday gave you trouble. 25 says find the total area. Area is a code word that means positive stuff only. So we'll have to do the graphing and stuff from yesterday to look at it. So total area, here's where we are, negative x squared minus 2x. To make any kind of graph of that, we'd have to factor. So negative x could come off, x plus 2 sits there. This would tell you we touch at the origin. This would tell you you touch at negative 2. So if I go to make a graph, 0 is a touch point, negative 2 is a touch point. X squareds are u's. We'd have to decide right side up or upside down. This one's upside down. Something like that. I know it's upside down because there's a negative with the x squared, or if you're not sure, just grab your calculator, graph it, and see. Then it said we were trying to go from negative 3 to positive 2. So if I need to go back to negative 3, I capture this. If I go as far as positive 2, I'm going to capture that. Okay, on that? So if I want to take on, where do I have board space to do this? I'll take a slide slightly to my right and do a little bit of erasing here. If I want this first underground piece, I'd go integral from negative 3 to negative 2 of this stuff. The middle piece, I would do integral from negative 2 to 0 of that stuff. The last piece, I'd go from 0 to 2 of that stuff. This one's going to have to turn up negative. This will have to turn up positive. This will have to turn up negative. If it doesn't, I made a mistake. I can see from the graph it's unders and then overs. Okay, that comes up so far. So antiderivative, negative 1/3 x cubed minus x squared. And I'm going to need to plug in from negative 3 to negative 2. This one, I'm going to have to plug in from negative 2 to 0, but it's the same thing. I don't want to write it again. This I'd have to plug in from 0 to 2, but it's the same thing. I don't want to write that again. If I put in negative 2, I get a negative 8 from cubing, negative times negative, that's positive 8/3, minus negative 3 squared is positive 9. That would be from the negative 2 plug in. Wait. Negative 2 squared is 4. So I got ahead of myself. So negative 2 plugged in is that. Minus negative 3 plugged in would be at negative 27 times a negative 1/3. That's a 9. Minus, plug in a negative 3. That's a 9. So that's a 0. So 8/3 minus 4, that's 8/3 minus 12/3, that's negative 4/3. Negative 4/3 minus 0 is negative 4/3. I thought I should get a negative. I can see from the graph, it's not that big. That sort of makes sense to me. For this one, if I plug in 0 to the antiderivative, the first group would have 0 minus 0. And when I go to plug in the negative 2, I don't really need to re-plug in negative 2. I just did that. A second ago, I plugged in negative 2, and the result I got there was negative 4/3. So I got a 0 minus a negative 4/3. That's 4/3. That's positive. That makes sense to me. My picture is maybe deceptive because this sure looks bigger than that, but my picture, I made no attempt to draw it to scale. I just drew a quick sketch. If you wanted more certainty on that, graph it on the calculator, and you'd be able to see a little bit better than my non-to-scale picture, but they're the same size. Then if I go from 0 to 2, I'd have to plug the 2 into this, which is negative 8/3 minus 4. Minus, if I plug in the 0, that was the stuff that just made 0 a second ago, I map this is -8/3 minus another 12/3, that's -20/3. And if I had a picture that was drawn to scale, I should be able to see that this is pretty gigantic compared to the earlier predecessors. It would just be big. For us to do the area, we want to add these up, but we have to add them up, making them all positive numbers. Change this to be positive, change this to be positive, and add them up in their positive form, and it would be 28/3. Not every hallmark problem in that section is going to have 3 partitions. Some of them might have like just 2. Some might have 3. It depends on the question and how they set it up. But 25 to 30 is that. The thing that makes some of these harder than others, some of the antiderivatives are just harder to do, like Rudy stuff, negative powers. That just makes your life a little harder to do the antiderivative and maybe to like do the plugins too. Worth a trig mention also would be something like if I sneak a 7 into this, you'd have to sneak a 7 into that and pay for that with a 1/7. We'll always divide by, when we're doing the antiderivatives, we're dividing by things. The derivatives are always multiplications, the chain rule multiply. Antiderivatives, you're going to be doing divisions of things. It's our day, it's 3:09, have some fun.